When grounding devices in patient care areas using either hospital-grade metal-clad cable or electrical metallic tubing conduit with a redundant ground wire, it is crucial to follow specific procedures to ensure patient and staff safety. The primary goal is to create a low impedance path to ground, minimizing the risk of electrical shock. Let's break down the proper techniques for each scenario. When using hospital-grade metal-clad cable, which invariably includes a ground wire, typically green or green with a yellow stripe, the following steps should be taken. Firstly, identify the ground wire within the metal-clad cable. This is usually easily distinguishable by its color. Secondly, carefully strip back the outer jacket of the metal-clad cable, exposing the insulated conductors and the ground wire. Use a cable ripper or appropriate tool to avoid damaging the insulation of the conductors. Thirdly, connect the metal-clad cable to the electrical box. Use an approved connector designed for metal-clad cable to ensure a secure mechanical and electrical connection to the box. Fourthly, create a pigtail connection. This involves connecting the ground wire from the metal-clad cable to the electrical box and then to the grounding terminal on the medical device. To do this, cut a short length of appropriately sized green insulated wire, typically number 12 or number 10 American wire gauge, depending on the circuit amperage. Fifthly, using a wire stripper, remove about 3/4 of an inch of insulation from the end of the ground wire in the metal-clad cable, one end of the pigtail wire, and the ground wire that will connect to the medical device. Sixthly, join these 3 wires together using an approved method such as a wire connector or crimp sleeve. If using a wire connector, ensure it is appropriately sized for the number and gauge of wires being joined and that it is listed for grounding purposes. Seventhly, securely twist the wire connector onto the exposed wires, ensuring a tight and reliable connection. If using a crimp sleeve, insert the exposed wires into the sleeve and crimp it tightly using a crimping tool designed for the sleeve size. Eighthly, connect the pigtail to the electrical box. Locate the green grounding screw inside the electrical box. This screw is specifically designated for grounding purposes. Ninthly, loop the free end of the pigtail wire around the green grounding screw in a clockwise direction. This ensures that when the screw is tightened, it will pull the wire tighter against the box. Tenthly, tighten the green grounding screw securely, ensuring that the pigtail wire is firmly clamped against the electrical box. This provides a reliable electrical connection between the ground wire, the electrical box, and ultimately the grounding system of the building. 11thly, connect the remaining ground wire to the medical device. Locate the grounding terminal on the medical device. This is typically a green screw or a terminal labeled with a ground symbol. 12thly, loop the free end of the ground wire around the grounding terminal in a clockwise direction. 13thly, tighten the grounding terminal securely, ensuring that the ground wire is firmly clamped to the device. This completes the grounding path from the metal-clad cable through the electrical box and to the medical device, providing a safe and reliable ground connection. Now let us consider electrical metallic tubing conduit with a redundant ground wire. When using electrical metallic tubing conduit with a redundant ground wire, which is an additional ground wire installed within a conduit, the grounding procedure is slightly different. Firstly, inspect the electrical metallic tubing conduit to ensure it is properly installed and that all connections are tight and secure. Electrical metallic tubing conduit relies on the mechanical connection between the conduit and the fittings to provide a ground path. Secondly, identify the redundant ground wire within the electrical metallic tubing conduit. This is typically a green or green with a yellow stripe insulated wire. Thirdly, connect the electrical metallic tubing conduit to the electrical box using approved connectors. Ensure that the connectors are properly tightened to provide a good mechanical and electrical connection. Fourthly, in this scenario, since the electrical metallic tubing conduit provides a continuous ground path, and a redundant ground wire is present, it is not strictly necessary to pigtail the ground wire from the conduit to the box. However, doing so provides an extra measure of safety and redundancy. Fifthly, if you choose to pigtail the ground wire, follow the same procedure as described for metal-clad cable. Cut a short length of appropriately sized green insulated wire, strip the ends, and connect it to the ground wire from the conduit, the electrical box grounding screw, and the ground wire that will connect to the medical device. Sixthly, connect the ground wire from the conduit to the medical device. Locate the grounding terminal on the medical device and connect the ground wire securely as described previously. Seventhly, whether or not you pigtail the ground wire from the conduit to the box, ensure that the electrical metallic tubing conduit itself is properly grounded. This typically involves connecting the conduit to a grounded metal enclosure or a grounding electrode conductor. Eighthly, regularly inspect the grounding system to ensure that all connections are tight and free from corrosion. Over time, connections can loosen or corrode, compromising the effectiveness of the grounding system. Ninthly, when selecting materials for grounding, always use components that are listed and labeled for grounding purposes. This ensures that they meet the required safety standards and are suitable for the intended application. Tenthly, consult with a qualified electrician or electrical engineer if you have any questions or concerns about grounding requirements. Grounding is a critical aspect of electrical safety, and it is essential to ensure that it is done correctly. 11thly, always refer to the latest edition of the National Electrical Code, or NEC, and any applicable local codes and regulations for specific requirements related to grounding in healthcare facilities. The National Electrical Code provides detailed guidance on grounding methods, conductor sizing, and other important considerations. 12thly, hospital-grade receptacles and plugs are designed to provide a more secure and reliable connection than standard receptacles and plugs. They are typically used in patient care areas where the reliability of the electrical connection is critical. 13thly, when installing hospital-grade receptacles, ensure that they are properly grounded to the electrical box. The receptacle will have a green grounding screw that must be connected to the grounding conductor. 14thly, regularly test the grounding system to ensure that it is functioning properly. This can be done using a ground impedance tester, which measures the resistance of the grounding path. 15thly, keep accurate records of all grounding system inspections, tests, and maintenance. This documentation can be helpful in identifying potential problems and ensuring that the grounding system is properly maintained. 16thly, consider the potential for electromagnetic interference, or EMI, when designing and installing grounding systems in healthcare facilities. EMI can interfere with the operation of sensitive medical equipment. 17thly, proper grounding can help to minimize EMI by providing a low impedance path for unwanted electrical noise. 18thly, in some cases, it may be necessary to use shielded cables or other EMI mitigation techniques to further reduce the risk of interference. 19thly, remember that grounding is not a substitute for other safety measures, such as the use of ground fault circuit interrupters, or GFCIs. Ground fault circuit interrupters are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. 20thly, ground fault circuit interrupters should be installed in all areas where there is a risk of electrical shock, such as bathrooms and near sinks. 21stly, proper grounding is essential for the safe and reliable operation of electrical equipment in healthcare facilities. By following these guidelines, you can help to ensure that patients and staff are protected from electrical hazard. 22ndly, the NEC Article 517. 13 covers grounding requirements for healthcare facilities. 23rdly, it is important to understand the difference between equipment grounding and bonding. 24thly, equipment grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device, such as a circuit breaker, to trip and energize the circuit. 25thly, bonding, on the other hand, connects different metal parts together to equalize their potential and prevent voltage differences that could create a shock hazard. 26thly, in healthcare facilities, it is often necessary to use isolated ground receptacles. 27thly, isolated ground receptacles have a separate grounding conductor that is not connected to the electrical box. 28thly, this helps to reduce electrical noise and interference that can affect sensitive medical equipment. 29thly, when using isolated ground receptacles, it is important to follow the manufacturer's instructions carefully to ensure that they are properly installed. 30thly, The grounding conductor for an isolated ground receptacle must be run directly back to the grounding bus in the electrical panel. 31stly, it is also important to consider the impact of harmonics on grounding systems in healthcare facilities. 32ndly, harmonics are distorted waveforms that can be generated by electronic equipment, such as computers and medical imaging devices. 33rdly, harmonics can cause overheating of grounding conductors and equipment, as well as other problems. 34thly, to mitigate the effects of harmonics, it may be necessary to use oversized grounding conductors or harmonic filters. 35thly, it is crucial to maintain a complete and up-to-date set of electrical drawings for the healthcare facility. 36thly, these drawings should show the location of all grounding conductors, equipment, and bonding connections. 37thly, the electrical drawings should be readily available to qualified personnel who are responsible for maintaining the electrical system. 38thly, regular training is essential for all personnel who work on electrical systems in healthcare facilities. 39thly, this training should cover topics such as grounding, bonding, electrical safety, and the use of personal protective equipment, or PPE. 40thly, personnel should be trained to recognize and avoid electrical hazards. 41stly, ensure that all electrical equipment is properly labeled with its voltage and amperage ratings. 42ndly, this information is important for selecting the correct size grounding conductors and overcurrent protection devices. 43rdly, the labeling should be durable and easy to read. 44thly, when performing any electrical work, always to energize the circuit before starting. 45thly, use a voltage tester to verify that the circuit is de-energized. 46thly, lock out and tag out the circuit breaker to prevent accidental re-energization. 47thly, wear appropriate personal protective equipment, such as safety glasses and gloves. 48thly, use insulated tools to avoid contact with live electrical parts. 49thly, never work alone on electrical systems. 50thly, have another person present who can assist you in case of an emergency. 51stly, if you are not qualified to perform electrical work, do not attempt to do so. 52ndly, hire a qualified electrician to perform the work. 53rdly, remember that electrical safety is everyone's responsibility. 54thly, by following these guidelines, you can help to prevent electrical accidents and injuries in healthcare facilities. 55thly, the impedance of the grounding electrode system should be tested periodically to ensure that it meets the requirements of the NEC. 56thly, high impedance can indicate a problem with the grounding electrode system, such as corrosion or loose connections. 57thly, the grounding electrode system should be inspected regularly for signs of damage or deterioration. 58thly, any damaged or deteriorated component should be replaced promptly. 59thly, when installing new electrical equipment, ensure that it is properly grounded before it is put into service. 60thly, check the equipment for proper grounding connections and verify that the grounding conductor is properly sized. 61stly, when making any modifications to the electrical system, ensure that the grounding system is not compromised. 62ndly, any modifications to the electrical system must comply with the requirements of the NEC and other applicable codes and regulations. 63rdly, in some cases, it may be necessary to install supplemental grounding electrodes to improve the performance of the grounding system. 64thly, supplemental grounding electrodes should be installed in accordance with the requirements of the NEC. 65thly, it is important to coordinate grounding and bonding with other systems such as the fire alarm system and the telecommunications system. 66thly, these systems must be properly grounded and bonded to prevent ground loops and other problems. 67thly, ground loops can cause electrical noise and interference that can affect sensitive electronic equipment. 68thly, proper grounding and bonding can help to minimize the risk of ground loops. 69thly, the use of surge protective devices, or SPDs, can help to protect electrical equipment from voltage surges. 70thly, voltage surges can be caused by lightning, utility switching, or other events. 71st, surge protective devices should be installed at the service entrance and at other strategic locations throughout the electrical system. 72nd, the SBD should be properly grounded to ensure that they can effectively divert surge current to ground. 73rd, it is important to select SVD that are appropriate for the voltage and amperage of the electrical system. 74th, follow manufacturer's instructions for installation and maintenance of surge protective devices. 75th, consider the use of uninterruptible power supplies, or UPSs, for critical medical equipment. 76th, uninterruptible power supplies provide backup power in the event of a power outage. 77th, they can also help to protect equipment from voltage sags and surges. 78th, uninterruptible power supplies should be properly grounded to ensure that they can function properly. 79th, regular maintenance of the grounding system is essential for ensuring its continued effectiveness. 80th, this maintenance should include periodic inspections, testing, and cleaning. 81st, any problems that are identified during maintenance should be corrected promptly. 82nd, keep a record of all maintenance activities. 83rd, it's important to understand the role of the impedance of the grounding conductors. 84th, lower impedance grounding conductors provide a better path for fault current to flow, which helps to ensure that overcurrent protection devices will trip quickly and clear the fault. 85th, the National Electrical Code specifies the minimum size of grounding conductors based on the size of the overcurrent protection device. 86th, use appropriately sized grounding conductors. 87th, larger grounding conductors have lower impedance. 88th, when installing grounding conductors, avoid sharp bends or kinks, which can increase the impedance. 89th, route grounding conductors as directly as possible. 90th, when connecting grounding conductors to equipment or grounding electrodes, use approved connectors and techniques. 91st, ensure that the connections are tight and free from corrosion. 92nd, the effectiveness of a grounding system depends on the quality of the connections. 93rd, consider using exothermic welding to create permanent, low-impedance connections. 94th, exothermic welding involves using a chemical reaction to create a molten metal joint that fuses the conductors together. 95th, exothermic welds provide a reliable, corrosion-resistant connection that will last for many years. 96th, follow the manufacturer's instructions carefully when performing exothermic welding. 97th, it is important to use the proper materials and equipment for the job. 98th, inspect exothermic welds to ensure that they are properly formed and that there are no defects. 99th, another important aspect of grounding is the concept of equipotential bonding. 100th, equipotential bonding involves connecting all metal parts within a given area together to equalize their potential. 101st, this helps to prevent voltage differences that could create a shock hazard. 102nd, equipotential bonding is particularly important in areas where patients are likely to come into contact with multiple metal surfaces, such as operating rooms and intensive care units. 103rd, the NEC specifies requirements for equipotential bonding in healthcare facilities. 104th, these requirements are designed to ensure that all metal parts are properly bonded together. 105th, when performing equipotential bonding, use appropriately sized bonding conductors and connectors. 106th, ensure that the connections are tight and free from corrosion. 107th, test the equipotential bonding system to ensure that it is functioning properly. 108th, the resistance between any two metal parts within the bonded area should be less than a specified value, typically 0. 1 ohms. 109th, document the results of the testing. 110th, regular inspections and testing of the grounding and bonding systems are essential for ensuring their continued effectiveness. 111th, these inspections and tests should be performed by qualified personnel. 112th, any problems that are identified during inspections or tests should be corrected promptly. 113th, keep a record of all inspections and tests. 114thly, by following these guidelines, healthcare facilities can ensure that their electrical systems are properly grounded and bonded, protecting patients and staff from electrical hazards. 115thly, in summary, grounding and bonding are critical aspects of electrical safety in healthcare facilities. 116thly, proper grounding and bonding can help to prevent electrical shock, minimize electrical noise, and protect equipment from damage. 117thly, healthcare facilities should follow the requirements of the NEC and other applicable codes and regulations to ensure that their electrical systems are properly grounded and bonded. 118thly, regular inspections, testing, and maintenance are essential for ensuring the continued effectiveness of the grounding and bonding systems. 119thly, all personnel who work on electrical systems in healthcare facilities should be properly trained in grounding and bonding techniques. 120thly, by taking these steps, healthcare facilities can create a safer environment for patients and staff.